Hi and welcome back to the channel. In my previous video, we looked at how we can build a game from the ground up using only SDL3 and some associated libraries. The level editing, though, was very simplistic and not something you can use to build interesting game levels. In this video, though, we're going to look at how you can build, parse, and load game levels made with the tiled level editor and load them into our custom game engine. If you've never heard of Tiled, it's an excellent application that provides level editing that's not tied to any particular engine. It's packed full of features and will certainly make its way back onto the channel in future videos. The previous video, where we built the game from scratch, is not a required watch for this video, but I highly recommend checking it out because it's densely packed with content and an excellent watch for anyone looking to build their own game or game engine from scratch. And now with the formalities out of the way, let's get to work. Let's kick things off by downloading and installing the application. Tiled is completely free, but you can still support the project by paying whatever you feel comfortable with upfront. If you'd prefer to support the project later, simply click to take me to the downloads link at the top and download the installer for your platform. Once you fire up Tiled, you'll be met with this screen. Let's start off by creating a new project. I recommend creating a folder for the project, just like my SDL3 demo folder here. This way, you can keep all project-related files together. Then give the project file whatever name you'd like and hit save. The tiled project represents the working collection of maps and tile sets that we'll be creating for our game. Now let's create a tile set that we can use to start painting our map. Click the New Tile Set button and be sure to set the type to Collection of Images. This will let us add individual images to our tile set instead of one large sprite atlas. Enter the file name for the new tile set and save it in our project folder. Now click the plus icon in the toolbar and add the individual tile images to our new tile set. The reason we're using individual images instead of a single sprite atlas is because tiled sprite sheets need to be uniform grids, and you must be very careful about maintaining tile order after you've started using them on your maps. Meaning you could very easily break your map by adding sprites to your tile set. For me personally, this is a very cumbersome workflow, and since I don't have my tile sheets 100% finished up front, I refuse to work that way. In an upcoming video, I'll show how we can deal with this dynamically in-game and get the benefits of a single atlas without imposing those workflow restrictions during map design. For now, we stick with individual images and keep our work light. Click Save, and let's start painting our first map. You can close the tile set here and click the New Map button, or just go to File, New, and then New Map. Ensure the tile size is set to whatever your individual tile dimensions are. In my case, I'm using 32 by 32. The rest of the options can stay in their default values for now. Ensure the map is set to orthogonal, CSV is the tile layer format, and it's a fixed size. We now have a blank canvas to paint our map onto. Let's start by naming the current layer to level, which will contain all the tiles that the character walks on. If you're not seeing the new tile set in the bottom right, which is what's happening to me right now, just double click the tile set in the project listing on the left to open it, and then it should show up in the map as well. Make sure that the stamp tool is selected in the toolbar, or just press the B key, and select the tile to paint with in our tile set pane. I'm going to draw a small map, starting with the ground tiles, and then I'll add some of the panel tiles. Right now it's probably a good time to save our map so we don't lose any work. The layers in Tiled work just like in other layer-based tools. Layers on the top are drawn on top of layers underneath. Since I'd like to add a background and foreground layer, I'll place the background layer at the bottom of the list and the foreground layer at the top. Then if I click my background layer, I can start painting those elements as well. Don't forget that if you have a closed off tile area like you see here, you can quickly fill the space using the fill brush in the toolbar or hitting the F key. This is a time saver when you're filling a large area. Let's add some foreground elements as well. These are drawn over top of everything else. The background and foreground layers will be just there for aesthetics. The level layer is the one that our player walks on and collides with. I'd like to add one of these computer tile images in the background, but since I've already got a brick texture there, I can't. Though that's easy to solve, I'll just add another layer called background objects, which will give me another layer to decorate my map with. Now that we've seen how tile layers work, let's look at object layers. This type of layer is used for placing things on the map that aren't going to be part of the basic level tiles. This could be enemy positions, item positions, player start areas, event triggers, etc. I'll keep it simple for now and add a layer called characters. It's here that I'll place various game entities such as our player's position and enemy positions. Object layers don't have to contain only one object type. As you'll see here, once you place the object shape, you can give it a custom class name, which we can then look up in our code and decide what type of entity to spawn. So I select the Insert Rectangle tool and place an object in the layer for our player start position. After placing the object, it's important to specify a name and class in the properties pane. The class is how we'll know what to create in-game, and the name just makes it easy to see on screen what type of object it is. You can also create individual layers for different object types. This would allow you to define specific layers with different spawner code in-game, meaning an enemies layer could be used to set up a class in-game that knows about spawning enemies, or an items layer that we can use to spawn specifically items. It's a simple concept, but it can help you organize your layers and code as the game grows. Since this demo project only really has a player and enemy type, I'll stick to the single characters layer and give individual objects class names. Let's add an enemy object as well, set its name and class, save our map, and we can move on to our C++ code to parse the map. The first thing we should do is make ourselves familiar with the structure of the map and tileset files. Tile traditionally stores everything in XML files, though nowadays it can also export in JSON. We'll be sticking to the standard XML format since it's the default, and I haven't had any issues with it. If we take a look at our TMX map file, at the top level we have the map element and its associated attributes. You'll probably recognize some of the settings you selected when you created the map file. We have the map style, its size, as well as the dimensions of the individual grid elements. Next, we take a look at the tileset element. The source attribute refers to the file containing the actual tileset definitions, and the first GID attribute stores the first global tile ID contained in the file. If we look inside the file itself, we see a zero-based ID on each tile element. This is the tile's local ID within the tile set itself. When we take the first GID number defined previously and add to it the local ID from each element, we get each tile's global ID. These global IDs are then used to refer to specific tiles when drawing the map. Since our tile set is based on a collection of images, each of our tile elements has an associated image element, whose source attribute tells us the absolute path to the image file. Later on, we'll be parsing this path and getting only the file name so that we can load the images from our game's data directory rather than relying on a fragile absolute path. The grid element above all the tiles simply states that we have a 2D flat orthogonal map, and each tile element should take up a single grid row and column. Moving on to the layer elements, each one contains an attribute for its ID, name, and dimensions. You'll notice that these are the same layers we created inside tiled, except they're listed in reverse from how we set them up inside of the tiled application. Users of layer-based applications such as Photoshop or Substance Painter will be comfortable with the idea of layers stacking on top of each other from the bottom to the top. But when you're drawing these layers inside of your game, you're going to want to load them into a list and then iterate through that list each frame, drawing each layer. This is why having this list in reverse here is good for us. We start at the beginning of the list, drawing the bottommost layer first, and then iterate through each one, drawing them on top of one another, until we finish the topmost layer, which is at the bottom of the list, essentially in reverse from how the UI displays them. So we see the tile layers listed as layer XML elements, as well as the character object layer represented by an object group element, clearly demonstrated by the player and enemy elements listed inside. The objects are positioned using X and Y coordinates, letting us place them completely arbitrarily, rather than using a row and column within the map grid. Let's expand one of the layer elements further and look at the data element contained within. If you've gone through my previous video, you would see that this looks quite similar to the map representation I created in that video. A grid of numbers, the same dimensions as a map layer, with numbers referring to global tile IDs. In my original approach, I simply use numbers to represent object types in-game, which is essentially the same thing. In order to parse the XML, we'll use a library called TinyXML2. It's super easy to add to the project and very straightforward to use. The library docs explicitly tell us to just include the library sources into our project and compile everything as part of our application. That's about as easy as it gets. Head over to the TinyXML GitHub repo, go to the releases section, and download and extract the source code to your disk. Now we can add them into our project directly. So to do that, we can just create a folder called ext for external libraries and add the files inside of a subdirectory called tinyxml2. Then all we have to do is tell CMake to compile the source file and also where to find the header file. Since the library is also properly set up for use as a CMake package, and because I'm not a fan of adding library sources directly into my projects, I'll build the library and install it so I can find it with CMake. To do this, simply cd into the project source code, tell CMake to generate a debug or release build, and then actually compile the project. Visual Studio users need to also remember that they can specify the build type using the --config directive. Once the code is built, you run the --install directive and install the library somewhere on your disk. To link with the library, we head over to our CMake list.txt file and first call find package with tinyxml2 marked as required. Then we can add the tinyxml2 library to our list and target link libraries. CMake also needs to know where to find the installed package, and we tell it where using the CMake prefix path variable. If you need more details on this stuff, I have plenty of videos describing the process in a lot of detail on my channel. Check the description for more. With TinyXML set up, let's add some types to hold the map information that we're going to be loading. I've created a file called tmx.h, which is where we'll declare all of the structs we'll need to represent the XML map in memory. First, we include some headers that we're going to need from the C++ standard library, and then add a namespace for the types we're about to create. The first three types are used to represent the map layers. We have the layer struct, which will hold the various numbers representing the tiles used in a layer. The object group struct represents the object layers in our map, and they contain an array of layer object instances which represent the individual objects defined in the layer. The next three types will be used for loading the tile sets. We'll look at them from the bottom to the top. We have the top level tile set struct, which should have some familiar fields. There's the total tile count, the tile dimensions, the number of columns in the tile set, and the first global tile ID represented in the tile set. You'll recall that individual tile elements have a local tile ID, always starting from 0. When you add the local tile ID to the first global ID, you get each tile's global tile ID. And it's the global IDs that are referred to by each layer's data element. We'll see more about this further in the video. The tiles vector will contain the individual tile elements, and each tile has its local ID as well as an image instance which stores the path to the image file to load and its dimensions. The image paths contain the full absolute path to the individual tile images, and we're going to handle those paths appropriately later on. Wrapping everything up is the map struct, which is used to store the map dimensions, tile dimensions, a vector holding the map's tile sets, as well as the list of layer objects. Note that I'm using std variant in order to keep a single homogeneous list of layers. Variant is basically like a union, except that it's tagged and it knows what type it's holding at any given time. In this example, the variant can either be a layer or an object group type, and we'll be using std visit to process each layer depending on its type later on. If you watched my recent Making a Game from Scratch video, you would recall how we used a union type paired with an enum inside of our game object struct, letting us maintain a single memory-packed list of game objects while avoiding inheritance and polymorphism. At the bottom is a declaration for our load map function, which will return a unique pointer to the map object. Now with the types in place, let's take a look at how to parse the XML. We'll add a tmx.cpp file to our project, include the header file inside, as well as the TinyXML2 header, SDL file system, and the stream headers. We're ready to parse the XML now. Let's write the load map function. All the classes in TinyXML2 are stored in the TinyXML2 namespace. We'll start with a using statement first to keep the code more concise. We'll then take the string holding the map path and convert it to a file system path object. This will let us extract path information further in the code. Next, we can create an instance of XML document and use its load file method to load the map file into memory so we can traverse it. Then we can grab the root map element out of the document. We create an instance of our own map class so we can start filling it with data. We start with the map and tile dimension attributes of the root map element. Then we can focus on the map's child elements. The ones we're concerned with for now are tile set, layer, and object group. We'll process each one by iterating using a for loop, initializing the child element pointer by calling the map's first child element method, and then getting the next child element by calling next sibling element on every child's pointer. We do this until next sibling element returns a null pointer, letting us know that we're done with the child elements. We then check the name of each element and decide how to process it. In the case of a tileset element, we retrieve the first global tile ID as well as the source attribute, which tells us what file we need to load for the tileset's tile list. In order to properly find that tileset file, we'll use the file system path variable we created at the top of the function. The file system path class lets us break a path down into individual portions and extract what we need. Since the tileset's tsx file is in the same folder as the tmx file we're currently loading, we'll get the parent path of the map file, which is the directory that both files are stored in, and simply append the tileset file name. Once we load the tsx file, we get its root tileset element and retrieve the attributes detailing the tile dimensions, tile count, and column count. Then we can create an instance of the tileset struct and start filling it with tile objects. We iterate through the tileset's tile child elements the same way we did previously. For loop starting with the tileset's first child, then progressing forward using each child's next sibling element method. For each tile element, retrieve the associated image element, which gives us the absolute image path and its dimensions. With the image details loaded, we can push the current tile into the tileset. Once all tile elements have been processed, move the new tileset object into the map's tileset's vector using the std_move function. This prevents copying of the tileset object when adding it to the map's tileset's vector. The next child type is the layer element. These are the map's tile layers and their associated tiles, grid placements. We get the layer's name and ID, then reserve memory in the layer object's data vector, making space for the integers in the layer's data field. We ask the vector to make space for the grid of integers, the size of which is the product of the map grid's width and height. The reserve call pre-allocates memory up front, making sure that we don't have to reallocate the vector and copy its data repeatedly as we step through the comma-separated integers in the layer's data field in the upcoming code. The interesting bit of code here is how we read the CSV data. We use an std string stream to go over the block of comma-separated values, reading in each integer and ignoring any commas. Once we finish streaming in the block of integers, we move the layer object into our map object and continue. The last child type we'll handle is the object group, representing object layers. This is the simplest one to load. We get the layer's ID, name, and then iterate through its child object elements. For each child object in the group, get its ID, coordinates, as well as the name and class strings we specified when placing them on the map. Once we're done adding each object into the object group layer, we once again move the object layer into our map. Now we can just wrap our map object pointer with a unique pointer and return it. And since we're now done writing our XML parsing code, let's get the map loaded in the game code and process the level. First start by adding std file system and the tmx.h headers. Then head down to the game resources struct. All of this code was written for my recent SDL3 game from scratch video. Check that out if you haven't already done so. As expected, we'll hang on to the loaded map using a unique pointer, which simply means that there should only exist a single owner of this map object pointer, and that's the resources struct. Any attempt to copy this pointer, or the resources object for that matter, will result in a compilation error. If any other code must hold its own copy of this pointer, then the ownership wouldn't be considered unique, and a shared pointer would be more appropriate. In order to associate the tile set's available tiles with SDL texture objects, we'll need a simple struct called tilesetTextures, which holds the first GID of the tile set and a vector of SDL texture pointers representing each tile. We'll add another member vector to our resources struct, which can hold a tileset textures object for any tilesets that are present on the map. Though in this case, we only have one. Now we can call the load map function and store the resulting pointer in our new member variable. Then we need to process the associated tilesets and load the images into GPU memory. As we work through each tileset object, we create a matching tileset textures object. We copy the first GID variable and again use the reserve method to pre-allocate memory in its associated texture pointers vector. Now we need to iterate through the tileset's tile objects. As I mentioned earlier, the image paths are the absolute paths on the hard disk. What I want to do though is get the file name and tell the program to find a file with a matching file name in my game's data directory. The handy file system path class can once again be of use here. We create a path object based on the image source path, then call the file name method on the resulting path object and get just the file name. All I need to do then is concatenate the file name to the base path that I want the tile images to be loaded from. This bit of code simply makes sure that the game isn't trying to load files from various locations on disk, but rather always tries to find its resources in predictable locations inside the game's data folder. With the new image path produced, we call the load texture method, which uses the SDL image library to load images from disk, keeps track of loaded textures for cleanup later, and returns their pointers to the calling code. The SDL texture pointer gets pushed to the tileset textures object, and at the end of the loop, we end up with a list of SDL textures the same size and order as the tiles in the tileset object. When we're done processing a tileset in the map, we move the new tileset textures object into the resources member vector. With the map and tilesets now loaded into our game, we need to go through all the various layers and create the game objects representing what we drew inside tiled. We'll take a look at the game's game state struct, which is where all the game objects and game state resides. The previous game state configuration had a hard-coded set of game layers. This isn't very versatile and doesn't let us do anything creative with our maps. With the new setup, we have a vector of layers, each of which is itself a vector of game object instances. With this setup, we can add as many layers as we want in our game without any hard-coded restrictions. The player index was previously cached so that we can get the player object quickly using the player method. Now it also caches the index of the layer that the player resides in, since we don't know upfront how many layers there are on the map and what order they're in. Drawing the layers is as simple as iterating over all the layer vectors, drawing the game objects inside using the drawObject function. In order to draw the tiles, the drawObject function simply draws the SDL texture pointed to by each game object at the specified location. The full drawObject function does a lot more, drawing the appropriate animation frame, flashing sprites that are taking damage, debugging information, and etc. If you want to see how this was all built, check out the previous video linked in the description. Now it's time to actually create the game objects. In my createTiles function, I first create a layer visitor struct. I've declared it inside of the function because I want all of this code in one place. The struct will hold references to the various state objects of the game, as well as a couple of overloads of the function call operator. We create a call operator overload for each type specified in the std variant that we created earlier. That would be the layer and object group types, representing the two layer types that we have inside tiled. After declaring the struct, we iterate through each map's layers and use std_visit, giving it a reference to our layer visitor object, as well as an instance of an std variant, which at runtime would be either one of those two layer types. If you're not familiar with the visitor pattern, it's a form of dynamic dispatch, allowing us to execute different function overloads based on an object's concrete type. Visitor pattern is usually implemented using derived classes and polymorphism, but I quite like this approach using std variant. It lets us keep all the layers inside of a single vector without any base pointers or heap allocations. There's also quite a bit less boilerplate in setting this all up. We simply declare a vector of layer variants, we create our visitor struct with a couple of different methods, and just call std_visit on all of the objects. All of that related code is in one place and easy to maintain. You can make it even more concise using C++ lambdas, but that requires some templating and an explanation that we'll save for another video. To process a regular tile layer, we first tackle the TMX layer overload. Start by creating a vector of game objects to hold anything that we need on this layer. Then we add a couple of for loops to iterate over each row and column in the map layer. We use the row and column values to index into the layer's data vector, the comma-separated grid of numbers that we parsed earlier. If the global tile ID is not 0, this means that we have a tile placement. We need to look through our tile textures vector and find the appropriate SDL texture to represent the current tile that we need to create. We can use the std findIf function to look through the tile sets, and what we need to find is the tile set containing the current global tile ID. FindIf takes a lambda, which returns true if the current tile ID is within the range of tile IDs provided by the current tile set. When we find the appropriate tileset textures object, we take a reference to it using the returned iterator. Then we grab the texture using the global tile ID by subtracting from it the first global tile ID in the tile set, resulting in a 0-based local tile ID, or more simply, the tile index, which we can use to look up the SDL texture inside of the textures vector. Once we have the texture, we can call the createObject function using the row and column numbers, the tile's texture, and specifying the object type as level. The createObject method just sets up some common fields on each object, like their type, calculating their x and y coordinates based on their row and column, the texture, and a default collider. Straightforward stuff. In the case that we're not looking at a level tile, I'm simply zeroing out the collider dimensions to ensure that they don't cause any collisions. We don't want foreground and background tiles to result in collision responses. This is a very simplistic way of differentiating between non-collidable tiles and collidable ones, but it'll suffice for now. It's also not super performant, but in an upcoming video, we'll look at how we can use collider boxes defined directly inside of tiled to handle the collidable areas of the map. We then push the created object into the new layer vector, and when we finish going through all of the rows and columns, we can move the newly created layer into our GameState's layers vector. Processing the object layers is somewhat similar. In this case, we iterate through the layer object instances inside of the object group layers. Once again, we create a vector of game objects to hold the required objects for this layer. Since tiled objects use x and y coordinates rather than row and column pairs for placement, we use those directly for placing our new objects. The only difference is that we subtract the half width and half height from each coordinate respectively, because tiled's coordinates are in the center of the object, and the game that we've built here expects its coordinates in the top left. Checking the object type variable tells us what object we need to create. We only have a player and enemy types added to our map, so there is an if-else chain to handle each case. These objects are slightly more involved to create since they define custom collider values, animations, and movement-related data. For a thorough explanation of how this was all built, once again, please check out the Game Dev from Scratch video linked in the description. We go through building all of this, and this video would end up being far too long if I had to recover everything I've covered in that video, so please check it out. After creating the appropriate object, we push it into the new layer vector, and when we're done processing all the layer objects, we move the new layer vector into our game state as well. Now that we've loaded the map tiles and objects, we can run the game and see the map replicated and playable in our own game engine. Everything seems to work quite well, and we can start thinking about what new features, items, or characters we should add to make this proof of concept into an actual fun game. The thing we still need to discuss though is that we've only really built a tiny little map with a small number of tiles. How will this game engine perform in its current state if we throw a larger map at it like this? Let's give it a shot. Well, it performs abysmally, and because of the added lag in our frame processing, our physics and collision detection simulation are now broken. We'll create a better game loop in the future that'll be more resilient to frame drops, but the bad performance is a separate problem altogether. This is almost exclusively caused by the collision detection code. It's extremely naive in that it checks every single game object against every single game object, even ones that don't have colliders. In my next video, I'll show you how to split up the map using a quad tree in order to make better decisions about which object collisions we should check for. But for the moment, let's make use of some low-hanging fruit. First, let's take a look at the loop that updates our objects. We're currently iterating over every single object in the game, and most of our objects don't actually move at all. They're just stationary tiles. The game object struct has a field that tells the engine whether an object is dynamic or not. which we're currently using to prevent objects from being pushed down by gravity that don't need to have gravity applied on them. Let's just wrap the call to update with a check if an object is dynamic. This alone will eliminate the performance problem we're dealing with. But there's one more thing I want to tweak. As you recall, we're zeroing out the collider dimensions of tiles that are in the background and foreground since we don't want anything colliding with them. They're just decorative. But the engine will still check those tiles for a collision, and will always result in no collision, which is just a pointless check. If you can imagine a map with a lot of background graphics and foreground tiles like grass or objects, etc., that's a lot of pointless checking. Let's change the collision checking to never even test objects that have colliders with zeros in their width and height fields. And now if we run the game, we see that it runs much better. These changes will go far in allowing us to create much bigger maps, so go ahead and get creative with your own game and enjoy making some interesting levels. Don't forget that in the upcoming videos, we'll be optimizing this code further, as well as making the rendering faster by grouping our images into a single sprite atlas, allowing the SDL3 renderer to draw many more tiles at once with a single draw call. This will make a big impact. And with that, I hope you enjoyed watching this video as much as I enjoyed making it. And if you did, please like and subscribe, and leave your thoughts down below. It really helps the channel grow. Let me know what topics you're interested in or what projects you're working on. I really like the feedback loop with my audience. Also, don't forget to check out my new Discord server where we can chat and show off our work. Thanks for watching, and I'll see you in the next one.